Start the recording, so don't forget to do that, because that's been my bugaboo like as long as recordings have existed. R equals 4 minus 4 sine theta. We're looking to create a table of values, and that table of values will be used to create the graph. And just like the last one, we want to go through the process while using the friendly R values. I'm sorry, theta values. I put all right, so the friendly values for sine are basically the ones that aren't friendly for cosine. We're disregarding the 45-degree reference angle ones because those aren't convenient for either of them. Those are great for tangent, so you can put that in your pocket. We have 0, pi over 6, pi over 2, anything on a quadrantal, so anything on a coordinate axis, so xy axis is going to be convenient for both. Actually convenient for all trig functions. 5 pi over 6. But it's basically the 30-degree reference angle, because we know sine of 30 degrees or sine of a 30-degree reference angle is going to be some kind of 1/2. It's just a question of positive or negative. So pi, we can go 7 pi over 6. We can go 3 pi over 2. We can go 11 pi over 6. But just like any other graph, you don't want to have to plot all the points. You just want to plot enough points to get a sense of what the trend is. Right? And once you've done that, oof, that line was so bad, and so is that one, that autocorrect could offer me nothing there.
I have a quick question.
Sure.
So when we're setting up a table like this, are these points kind of universally good to use for like plugins on all of the questions? If that makes any sense, like
they're universally good for sine functions.
For sine, okay.
Yeah, because if you look at the ones that we came up with for cosine, you see that we're looking at the 60-degree reference angles. And that's based off of the cleanliness of the results on the unit circle.
Okay, all right. Thank you.
No problem. So 4 minus 4 times the sine of 0. All right, on the x-axis, the sine function is always going to be equal to 0 because the y value of every coordinate on the unit circle is the sine function, all right? So sine of theta is the y value. And if it's specifically on the x-axis, that means that the y value is 0, making sine equal to 0. So you could actually just jump right in, since you know that this part is going to zero out and give you a result of 4. You can kind of jump right through and take note of any instance in which the function would be on the sorry, on the x-axis. For some reason, I didn't put the 2 pi there. You may not even need it, but I want to have it there. So I got my 4, got my 4. All right. The pi over 6. Now, I'm just going to jot down ASTC here, so I have something to point at. So we know that the sine function is positive in the first and second quadrants. All right. So the reference angles for sine, and actually let me do a different highlight color there. The reference angles for sine in those quadrants that are clean, again, are the 30-degree reference angles, or pi over 6. But those translate to the theta values of 5 pi over 6 and 5 pi over 6. So when I make this computation here, so this next computation is going to be 4 minus 4 sine of 1/2. I'll put that, fully getting ahead of myself. Pi over 6, which is going to be 1/2. It's really 4 minus 4 times 1/2, so 4 minus 2 is 2. So that tells me that this number is going to be 2 also, right? Because the sine of 5 pi over 6 is the same as the sine of pi over 6. So recognizing those relationships with the unit circle kind of help you to sort of trim the fat a little bit. Right? This is kind of bothering me. I'm just moving it a little bit. It shouldn't bother me, but it is. All right. So we got those values. Pi over 2, sine of pi over 2 is equal to 1. So 4 minus 4 times the sine of pi over 2. I'm writing out all the details here for instructional purposes, but by all means, you do it in your head, that's great. You know, there's no nice way to say this. There's no intelligence penalty in this class. Like, if you're smart enough to know this stuff in your head, you don't have to worry about, like, in an algebra class, I lost credit because I didn't show all the steps. That's not how it plays out here, right? So 4 minus 4 is going to be equal to 0. But again, if you could do that in your head, that's wonderful. Now, that being said, we have this and this guy. These are opposites of one another. They're on the opposite ends of the unit circle, but they also give sign values that are opposite of one another. All right, so if I were to say, all right, well, this was for pi over 2, it's 4 minus 4, then this one's going to be 4 plus 4. Because this is going to have an opposite value. So you can just kind of snag that piece of information right out of it. You know, so it's little tricks of the trade like that kind of streamline the process. Instead of you saying, man, it's more and more plug and chug, this is brutal. You know, it makes things a little bit easier. And it's the same idea holds true. Let me go blue for those people who are at home. You have, these give opposite results. Right, pi over 6 and 7 pi over 6, because the sine function is negative in the third and fourth quadrant. So in fact, it's also this one. So in the case of pi over 6, I was doing 4 minus 4 times positive 1/2. This would be 4 minus 4 times negative 1/2. Which is the same as, instead of 4 minus 2, it's going to be 4 plus 2. So that's going to give me a 6, and that's also going to give me a 6 here. All right, so you get to a point where just by knowledge of the unit circle, those relationships, all those important relationships that I've been harping on, you're able to kind of streamline the approach. Now, you take a look at some of these numbers and you start realizing, oh, sometimes I might have to scale these graphs. That's pretty interesting. I didn't really think that would be a thing for polar graphs. I thought that was only for XY coordinate systems. Well, it's like that for XY. It's like that for polar systems. It'll be like that in three-dimensional systems. Sometimes the numbers are big and you got to scale. So what we're going to do is we're going to go by 2s. And you don't want to have to label each one up. So what I'll do is I'll just say scale by 2. Now, that's going to require you to keep all this information straight, but you know, that just requires you to pay attention to detail. All right, and just remember, like in the previous example, you're plotting the points backwards. So r comma theta is what we're looking for. So we're going to have 4 comma 0, 2 comma pi over 6, and so on. All right. Now, when I plot 4 comma 0, that would normally be 4 steps in the direction of 0, but because I'm scaling by 2, it's going to be 2 steps in the direction of 0. So it's going to be right here. All right. Pi over 6, we would normally take 2 steps, but because we're scaling by 2, that's 1 step. As you get closer to the pole, it's a little bit trickier to get it precisely on the point that you want without hitting other points. So you just do the best you can. For the 0 pi over 2, that's 0 steps in the direction of any angle is still going to keep you at 0. So that's fine. 2 steps.
I'm sorry, Professor. You said pi over 6 is 2, right?
It's 2, but we're scaling by 2, so it's 1 step.
Okay. And the one that you put, there was pi over 12, I think, instead of pi over 6.
Yeah, that's what I was saying. It's kind of hard to get it like precisely on the point that you
Oh,
want.
yeah.
Yeah, so
Oh,
just
okay.
yeah. I try to smidge it up a little bit, I guess. It's still gonna be
Yeah.
like, not
Uh,
quite, but we'll
Thank you.
live with it. As long as it's in the neighborhood. All right. Then normally two steps in a direction of 5 pi over 6, but we're gonna do one step. That's gonna be like right here-ish. Just again, do the best you can. Sometimes you're gonna get a little spillover into some other angles. 4 comma pi. So normally 4 steps, but now 2 steps. And we really only scaled this to accommodate that R value of 8. Everything else seems to fit just fine. 6 steps in the direction of 7 pi over 6, which is going to amount to 3 steps in the direction of 7 pi over 6. So like that. Then we got 8 steps in the direction of 3 pi over 2, which is going to amount to 4 steps. So that's right here. And then 6 steps, so 3 steps in the direction of 11 pi over 6. And then the last one is 4 steps in the direction of 2 pi, so 2 steps. Well, we already got that. All right, so we completed the circuit, which is great. Now it's just a matter of actually drawing the figure. All right. So we got these points. We plotted them. We got the figure. We are going to have to do some calculus with this. So, but it's kind of like function-related mathematics, where you spend all these years building up your knowledge of functions so that you can apply that knowledge in the form of calculus, maybe some other areas of math and science. This is the same idea, except that's the one drawback of this course. You're kind of expected to learn all the foundational stuff immediately before learning how it's all applied. So that's the tricky part. You had years to master quadratics and trig equations and things like that. Now it's like, days. So, that could be a little daunting, but that's pretty much the long and short of it. Okay. So you kind of look up at the top here and you can see 4 minus 4 sine theta follows the model for Limason cardioid. All right. It's not a cardioid, but even though it kind of feels like it would be, because cardioid, it's a derivative of, like the cardi part, not that cardi, but like cardiac heart. That's really what it's talking about. And if this doesn't look like a heart, a mathematical heart, I don't know what does. In any kind of math class. But that's actually not a cardioid. It's a limason, a little cedilla under the C. It softens up the C, in case you're wondering how that's pronounced en français. So R equals A plus B cosine, A plus B sine theta tells us that the A and B values are different, right? Whereas in the cardioid, the two coefficients are exactly the same. They wouldn't be opposites of one another like we have in this case, all right? So 11 is a cardioid, 12 is a limason.
So because of that negative sign, it makes it a limason?
Correct. Sometimes that's all it takes. Now you get to something like, and this is the last one I'll do, because the rest are, I think, number 14 is definitely a direct variation of something like number 13. And 15 is actually easier than all of the ones that I've done. So it's just the kind of thing where I'll do number 13 because I think having a second look at this skill allows people to have a better handle on it. So I'll save those 2 problems to go over next time. All right, so I'll give people an opportunity to take another crack at it. Because I remember seeing this for the first time, and if you weren't comfortable with the unit circle, then there wasn't much I was saying last class related to that topic that was making sense. But if you took the time to study the unit circle between then and now, it's starting to make a little bit more sense. But it's still, in a lot of ways, just a lot of numbers that I'm pulling out of thin air. Having another look at it will make it a whole lot more manageable. So I really need to continuously stress the importance of the unit circle, because we'll get to a point in the course where you just can't fake it anymore. Right? You'll have to know it. And if you don't, you'll just get to a point where you're not getting stuff right, period. You know, so that's something to keep in mind, right? So yeah, I was gonna kind of think about cutting to the chase here, but how about I do it just like I did in the last one? All right, so theta 6 sine 2 theta and r. All right, and again, this is going to come down to knowledge of the unit circle, but again, we're looking for nice, convenient values for the sine function. However, we want sine of whatever 2 theta is to be convenient, all right? So this needs to result in a convenient value. Or a sine-friendly value. So it's not just a matter of saying, okay, I know that pi over 6 is a sine-friendly number. I need some number that's multiplied by 2 to give me pi over 6 as a result. All right, so now 0 is fine. 0 is going to give me a 0, so I'm not worried about that. But if I want to end up with a result of pi over 6, then I really want to be looking at pi over 12. All right, because pi over 12 times 2 pi over 12 is going to give me pi over 6. All right, now we just go along the values that are on this this circle that are given to us. You would say, okay, well, what's next? Pi over 6. If I put a pi over 6 in for theta there, I'm going to get pi over 3. No help there. Pi over 4, maybe that comes back into the party. If I put in a pi over 4 for theta, 2 times pi over 4 is pi over 2. So I want pi over 4 to be in my list. All right. Pi over 3, if I multiply that by 2, that's going to give me 2 pi over 3. It's the denominator that matters. All right. Because the denominator needs to be something like 2, 0, I mean, not 0 specifically, but the fraction should be 0, or 6, all right? So when I'm working my way around, I would look at pi over 2. If I put in a pi over 2 for theta, 2 times pi over 2 is pi. Anything that already has a denominator of 3 isn't going to work out. So I'm going to leave the 2 pi over 3 alone, because that's the best that's going to become is 4 pi over 3, all right? So 3 pi over 4, that would become 3 pi over 2. So I want 3 pi over 4 to be part of the party. Then if I look at 5 pi over 6, that would become, if I double it, 10 pi over 6, which becomes 5 pi over 3. So I don't want that one. But if I look at the next one would be 11 pi over 12, that becomes 11 pi over 6. That's fine, denominator 6. So I want 11 pi over 6 in the action here. All right. Now this is a fair few set of values here. I think at this point, what we want to start thinking about doing is maybe seeing where these numbers take us and use some symmetry. Maybe we'll get what we need. Let me take a look at the chat here and see some things going on here. Okay, study groups. Okay. Study groups, good. It's always a good idea. Never a bad idea. So, all right, but looks like that doesn't involve me. So I'm gonna put that away and then get in here. Yeah, never a bad idea for study groups. This class, definitely. All right. So 6 sine of 0, 2 times 0 is 0, sine of 0 is 0. So this, we're going to start off very nicely with 0, 0. Beautiful. All right, so that's good news. All right, then pi over 12, 2 times pi over 12. Again, the whole reason why we selected these numbers, sine pi over 6, because 2 times pi over 12 is pi over 6. Sine of pi over 6 is a half, times 6 is 3. Pi over 4, doubled is pi over 2. Sine of pi over 2 is 1, times 6 is 6. Pi, anything on the x-axis, like we talked about before, whether it's 0, pi, 2 pi, any multiple of pi is going to end up being a result of 0 in this case. All right, so I don't have to do the work there. 6 sine double 3 pi over 4 is 3 pi over 2, so negative 6. And then 6 sine double 11. Oh, you know what I did? I knew it was going to happen at some point. I meant to put the 11 pi over 12 here so that it would become 11 pi over 6. All right, and so that's going to be a negative 3. All right, because the sine of 11 pi over 6 is negative 1/2, and then there it is. All right, negative 1/2 times 6. So at this point, I'm going to start plotting and see where we end up. So, 6 is technically off the grid, but I'm fine with that. A little bit off the grid is okay. If it's way off the grid, then you want to think about scaling it. So 0 for an R value, doesn't matter what the angle is. The R value is 0, it's 0. 3 steps in the direction of pi over 12. I'm going to put me right around. 6 steps in the direction of pi over 4. So that's 1, 2, 3, 4, 5. I'll call this 6. All right. 0 steps in the direction of pi. No help there. Negative 6 in the direction of 3 pi over 4. So that's the first tricky one. All right. So that's telling me stand at the pole, face 3 pi over 4, but then take 6 steps in the opposite direction. All right. So 6 steps in the opposite direction is going to put me down over here. Same idea for 11 pi over 12. I'm taking 3 steps away from that. So find 11 pi over 12 and then take 3 steps in the opposite direction. All right. So we got a little symmetry going on, which is kind of, it's good and it's bad. It's one of those things, like if I knew it was symmetric over the x-axis going in, that would have been perfect. Because then I could have taken my 2 coordinates in the top half and plotted them to the bottom half without doing the calculations, but hindsight is 20/20. Verifying update is what my iPad says. This is scary stuff right now because it just shut down on me. All right, so let me pause the recording. So resume the recording. All right, yeah, so nothing messes up someone's train of thought quite like a technology issue. But regardless, so we need more points. That's the short answer here. And so we left off with 11 pi over 12. So then it's like, all right, well, maybe we continue on from there, And so, yeah, that's part of it. And at this moment, I realized, and I apologize for, oh, you gotta be kidding with me. Disconnect Apple Pencil. Now my Apple Pencil doesn't want to work. I'll try it now. Maybe just need it to reconnect. Oh, there's going to be a strongly worded email. Anyway, so yeah, I get flustered and this is what happens. That pi that I've highlighted there, that should have been a pi over 2. I apologize. So the whole idea, I kind of ran into the issue again of I wrote down in the column what I wanted it to be after I did the substitution. So I'm trying my best to make sure that that doesn't happen too frequently, but it's already happened twice. All that means to me is I got to be a little bit more careful. So yeah, I wanted it because we're working around the circle. I want to grab the ones that'll eventually end up being the clean ones or the convenient ones. All right. So the good news is, if there is, we do have a little bit of a trend here that we can work off of. Yeah, I need more points, but it seems like as I'm working my way around the circle, we know all the quadrantal ones are fine, but it also seems like any value that has a denominator of 4 or 12, and we could have figured that out after the first quadrant, but I like to do the first quadrant and then a little bit more to kind of confirm that I didn't screw up something in the first quadrant. Now, how did I know that I screwed up that pi over 2 instead of pi? Is because the next one, as I worked my way around, was supposed to be pi. And I looked at it, I was like, oh, wait a minute, I already got that one. So that was my indicator. So I'm going to put in a pi here, and when I type or pop that in here, it's going to be sine of 2 pi. All right, so sine of 2 pi, anything on the x-axis is going to be equal to 0. So no help there because we already have the ones that are at the pole. All right, so it is what it is. Sometimes you kind of spin your wheels for nothing, but if you can get a good one, then it'll get you where you need to go. So 13 pi over 12 and 5 pi over 4 are my next candidates. All right, so 6 sine, that's going to simplify to 13 pi over 6, and 6 sine 5 pi over 2. All right, now anything with a denominator of 2 is going to end up on the y-axis. All right, so it's just a question of what part of the y-axis. So that's where you kind of do your counting, because we know that this is 1 pi over 2 up here. This is 3 pi over 2, so it's odd. All right, so 1, 3. The next one would be 5 pi over 2. That's going to put you up here, back where it's a positive 1. All right, so I know that this number is going to be 6. But for that 13 pi over 6, now it's like, oh, whoa, that's not even within the unit circle. But if you follow the trends, so I'm going to count my way around here. I'll use a pick a different color. I'll use some kind of variation of pink. All right, so here's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6. You know, it doesn't say 8 pi over 6, but it reduces. 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. All right, that's 2 pi. If I want 13 pi over 6, I'm heading back to this location here. All right, and that's where sine is equal to a positive 1/2. So I end up with a 3 again. All right, so then it looks like maybe we're working in cycles here. So I had 0, 3, 6, then 0, -6, -3. I wonder if that's going to be the case again when I pick up some more points. But let's see where these ones plot. All right. So for the apologies. So for the 13 pi over 12, we're going 3 steps in that direction. That's going to put me here. Oops. For the 5 pi over 4, I'm taking 6 steps in that direction, so that's going to put me over here. All right. Now, symmetry being what it is, I can now rely on that because I know that it's symmetric over the x-axis. So I can plot this point by symmetry, and I can also plot this point, same idea.
Why is the 13 pi over 6 the opposite direction?
13 pi, well, it's 13 pi over 12. 3 steps in the direction of 13 pi over 12.
Right, yeah, why is it? Oh, right.
Yeah, because it became 13 pi over 6 when we plugged it in.
Okay, so why was the arrow pointing to pi over 6?
Oh, to help us with the computation, because that was to equate the 13 pi over 6 with pi over 6, which we knew would have the same value.
Okay.
Sine of pi over 6 is 1/2, so I knew that that would be the same number.
Okay.
All right, so we have some points here, and it's like, all right, well, we got a lot. It's just, do we have enough? All right. It does help if you have a little bit of a sense of the classical curves, but that chart on the previous page, you know, different people have different strengths and weaknesses, and I know that historically, as you know, I've been teaching this class for a while, people just don't want to memorize facts that they know aren't going to be things that they'll be using over and over and over and over again. And classical curves is not one of those things that you'll be coming back to over and over and over again for years. It's just like for this topic, for the next topic, you know. So, but the idea of plotting points on a polar coordinate system, that is something you would be coming back to, right? So you could rely on some shortcuts, but the better idea is to start thinking in terms of, you know, like how this would look when you start plotting, right? But yeah, I think we can start getting into the idea of maybe coming up with a sketch of this. It looks like if I'm starting at the pole, you do need to have some kind of prior knowledge. I can't get it through my head that my Apple Pencil is not working now. You're looking at something like that. Now, you wouldn't necessarily know that there's another point over here that exists unless you did a calculation, all right? So let's actually crunch out one of those calculations just to have it on paper. So we kind of go back and fill in some of the not convenient values, right? So we're finished with all the values around the circle that we deem to be convenient or sign friendly. Sometimes you have to dive into the ones that aren't really so sign friendly, you know, so maybe you get into like a pi over 6, a pi over 3, something like that. So, you know, just for the sake of actually, let me get rid of that curve so that we can draw it freshly in a minute. But let's say we took a look at the pi over 6 as a value. If I plug that in, 6 sine of pi over 3, sine of pi over 3 is radical 3 over 2. All right, so radical 3 over 2, decimal value, let's not worry about that just yet. Radical 3 over 2 multiplied by 3 is 3 radical 3. All right, so I'm going to plot 3 radical 3 in the direction of pi over 6. All right, I'll get to that in a minute, but let's take a look at pi over 6. I'm sorry, pi over 3. 6 sine of 2 pi over 3, you're going to see it's the same value. Because sine is positive in the first and second quadrants, same reference angles, the same value. All right. So now we just need to know what 3 radical 3 is equivalent to. All right. So it's just a matter of just crunching some numbers. So you can pull out a calculator, but then, you know, part of me is like, oh, if you're going to pull out a calculator, why not? Why wouldn't you have pulled out a calculator the whole time? So it's one of those double-edged kind of things. But if you're doing it for simple computations, there's nothing wrong with that. Let me just log in. Oh, this thing really forgot everything about me? Holy, oh, you know what, I'm on incognito. Am I on incognito? Yeah, I was on incognito. All right, so I just popped in a 3 radical 3. So it's about a little over 5. All right, so I'll just keep that up for later. So a little over 5 in the direction of pi over 6 and pi over 3. So I'm going to plot those points. 1, 2, 3, 4, 5. So it's going to be like right here and a little like right over here. All right, so that's good news because symmetry being what it is, we know that we're going to get a point, a little guy over in this neck of the woods and over here. And because it's fully symmetric over the y-axis, as you can kind of start getting a sense of, it isn't until you get a whole lot more points that you're really sure, but it does appear that what's happening on the right is also happening on the left. We have these points that we can rely on also. All right, so then I'm just going to snag one more. I'll pop in a 5 pi over 12, and then we'll know that that's going to be all around symmetrical also. Let me get the red pen again with the appropriate size. So 5 pi over 12. So 6 sine 5 pi over 6. Actually, kind of surprising that I missed that one somewhere along the way. Because that one actually would have been fine. That's also a 3. So that's going to give me a point 1, 2, 3 units here. And by symmetry, I know it's going to be here, here, and here. All right. Now there is a part of this where you just got to kind of have a sense what the function looks like. Classical curve chart, that'll do it. But you could also put it in a calculator, which I'll show you in a little bit, because there's part of this where it's like there's got to be an easier way. So this is going to be a 4-petaled rose. So here's one petal, right? We just need the other 3, right? So we're just going to repeat that process. It's in each quadrant, and I'm just going to. I can't see through my own fingers, so I guess in the grand scheme of things, that's probably a good thing. So you're looking at a graph that's going to look something like that. All right. Now, when you get into the calculus of it, you can kind of get a sense that there's a whole lot of shaking going on here. There's a lot of things that would happen. I mean, in terms of slopes, whew, a lot of things to analyze. But having a sense of it kind of tells me that if you can determine, in terms of rates of change, slopes of tangent lines and things like that, if you can determine everything there is to determine about the petal that's in the first quadrant, then you pretty much have everything that you need. And the question was, is this a rose? And it is. It's hard to believe. Doesn't look very rosy at all, but that's the figure known as a rose, right? The polar graph figure, right? So I'm gonna stop this recording because it's been